Okay, here we go again. This is the April 14th lecture of Introduction to Engineering. I am, of course, your genial host, the masked professor, also known as Harry Whiting. And we will be going through chapter 18, which is about green engineering. This coronavirus scare has really thrown us off in some ways, because ordinarily what I would do is I would have several days now where we would do a session on how to draw on the computer. In fact, we usually do a couple of sessions. We do a couple of sessions of reverse engineering, where we would take things apart and look at how they work. We would have days when y'all would just work on your project. Well, obviously, all of that goes by the board. So I'm praying I can create enough material till to carry us to the end of the semester. I mean, there's certainly a lot of material inside our book. All right, so green engineering is the idea of how do we use natural resources in a way that we create energy by robbing energy from nature. All right, so when we think about renewable sources of energy, the sun is sending us an awful lot of energy all the time. As you can see, it's listed here as about 2 times 10 to the 17th kilowatts. Oy vey. Now, that solar energy is absorbed and used in many ways. For example, it warms up the oceans. The oceans, of course, need to be warm. It goes into plants, and with carbon dioxide, they create, through photosynthesis, they create food that allows them to grow. So sometimes we're using solar energy by doing things like chopping up wood and burning it. Of course, when we do that, there is a certain large amount of particulate matter in the air from that. Right? Or eventually, some of that energy that's absorbed gets buried in the earth, turns into oil, and eventually is used. Although that is so slow that probably oil will be totally over by the time the current foliage turns into oil. All right, so how do we use these renewable sources of energy? Well, essentially, all these forms of energy come from the sun. So this number, 2 times 10 to the 17th power kilowatts, is what powers it all. It powers plants growing. It evaporates water that then is transported up to the higher elevations and comes back down, and we're able to make hydropower out of it. It makes oil. Everything essentially comes from the sun. Now I hear you say, well, what about nuclear power? We only have those radioactive particles, though, from the sun. So, take that. All right, so how do we use these renewable sources of energy? The direct sunlight we can use to make solar heating and photovoltaic power. Some of you may be studying in our renewable energy program and learning about photovoltaic power. And about 0.02% of sunlight is converted to wind energy every day, right? So that wind energy also comes from the sun. So our wind is powering windmills. Our weather cycle is dumping water up in the high elevations so that we can make hydroelectric power. Well, one thing is that we are hardly even using our renewable energy sources. Okay, so now these figures are probably somewhat old. They don't give any attribution of when this was made. All right, so we say that all energy sources that are used by man are 94.2 quadrillion. Good thing I had a Kleenex here. 94.2 quadrillion BTUs. Now, damn it, people, why couldn't you have done it in kilowatts so we could then compare it to our kilowatt number that we were given for the sun dropping on us every day. 39% is petroleum. Petroleum is used for cars, for trucks, to generate electricity a lot of times. So it is a major energy source. I know that in the Green New Deal, they're talking about having high-speed rail everywhere, and no one is going to have a car or an airplane. Mark me down as the most skeptical one. All right, nuclear energy is only about 8% of our slice of the pie. Coal is at 23%, natural gas at 23%, and renewable energy at 8%. Like I said, these numbers are probably old. I've been using this book for several years, so probably out of date, because you may have noticed we're trying to put coal plants out of commission. Why we're putting coal plants out of commission here in America, where they have gone through elaborate lengths to make them very low polluting, while at the same time we're allowing India and China to build 3,000 coal plants for electricity with no pollution controls. Well, let's not worry about it. Bloody hell. All right, so you'll notice solar is a tiny little 1%. Our geothermal comes in higher at 5%. Now, geothermal can be used in several ways. We can make electricity if we have a place where the magma, the liquid rock that is under us, is very close to the surface, and we can drill down, put in a thing where we're making steam to power a steam electric cycle. But often it's just used to heat people's houses. You could do that practically anywhere you live by digging a huge trench about 7 or 8 feet down and running pipes through it that you run water through, and the earth naturally heats up that water. Biomass is, well, essentially it's trees, bushes, things like that, that we either make into a biodiesel or in some other way turn it into fuel. Wind, they have at less than 0.5%. I have my doubts about that number because wind has become a huge way of generating electricity in recent years. And hydroelectric at 50%. When they began pursuing the electrification of America in the 1920s, one of the things they did was starting damming up pretty much any moving body of water they could, and having that produce electricity then. All right, so you can see this is a representative set of graphs here, although not necessarily an up-to-date picture, but at least it gives us a starting point to think about this. All right, so when we think about our green resources and how we use them, well, photovoltaics have become a very popular way. You may live near a place where they have a huge photovoltaic farm to make electricity. It's become very popular to put that on your house. That can make you totally energy independent, or even in a position to be selling back small amounts of power to the power company. These guys are saying the cost is relatively expensive, but that price has been coming down for years, and it has reached the point where really, as you can see, it's competitive with other kinds of energy. They would not be building those photovoltaic farms if they weren't going to make money off it. All right. There is solar thermal electric power plants. The very first solar energy collecting type of power plant was actually of this form. It was made by a French engineer in the 19th century in Egypt. And of course, he didn't produce a very efficient plant, but be fair, it was the first one. All right, so we use the direct sun there, and we use the sun to produce steam. It can be expensive depending on how we do it. If you have ever driven out to California, you may have seen where they have a huge installation of this kind, where they have tons and tons of mirrors that are all pointing at a target that collects that energy and is constantly turning water into steam. although sometimes we use a dual cycle, where the direct solar energy bouncing off those mirrors will actually heat up a salt or another conductive, and then in a separate loop it'll turn the water into steam. Solar thermal heat is a relatively cheap way to try and recover some of the sun's energy. Again, we use the direct sun. We use that usually in some kind of household use, or in recent years, commercial buildings have actually begun to do more capturing of the sun to heat the building. Windmills, well, of course, the wind is dependent on the sun. We have seen, or I hope y'all have seen, huge solar farms where we have a lot of windmills. Typically a windmill is anywhere from 250 megawatts to 500 megawatts each one. I guess it would be possible to do larger ones. I'm just not familiar with any. So there you go. Again, wind can be a good alternative for somebody who's out remote, where it's uneconomical to run power lines, but small wind generator can do them really good. Then there's hydropower. Again, that comes from hydroelectric dams or tidal power generators. In recent years, there's been a lot of experimentation on how to use wave action or tidal action to generate electricity. So we already have many large facilities around, such as Hoover Dam or Grand Coulee Dam. Of course, it's harder and harder to find an undammed river where you can put a hydropower. Depending on what size you need, it could be done with a relatively small water wheel, but that has really fallen into decline in recent years. The tidal power generators, there are, whether they work on the tides or wave action, there are actually a lot of places available in the world where that could be done. I don't think they've really begun to tap that in the way that they could. All right, so the photovoltaic type of electricity relies, surprisingly enough, on the photovoltaic effect. It was first explained by Einstein. He got the Nobel Prize for it. He should have got the Nobel Prize for relativity, but the physicist from the Nobel Committee didn't understand his work, and so he was passed over for that. The basic idea is, almost tripped over my chair there. We take a hot wire and we shine a light on it. We get an electric current, but the color of the light has to be blue, right? So violet and blue have enough energy to create that photovoltaic effect, right? And we spit on these other colors. Damn it, they're doing us no good whatsoever. All right, so in our photoelectric effect, this is the current. I know y'all may be barely able to see any of this. This is our color of light going this way, starting with infrared here and going up through blue and violet. You get a tiny bit of electricity right until we get to the right place above cyan, and then it jumps way, way up. All right, so our speed of light connects our gamma, which is the wavelength, and our frequency, which is nu. You may not be able to see that that is a funny looking V. It's the Greek letter nu. So that gamma times nu equals c, which is the speed of light. Although, boy, that does not seem like the right centimeters or 100ths. Okay, it seems like that's not right. So, nu equals cycles per second, or hertz. Hertz was a German physicist, so he got the cycles per second named after him. Planck, another German physicist, discovered the relationship that tells us the energy of a photon of light. So E, the energy, equals H times nu. So that H is what's called Planck's constant. And damn it, it's bothering me a lot that they don't say that. But I'm always willing. Oh, wait, one more thing. I actually already went through this and corrected several things because some of the equations were messed up in the presentation. All right, so E equals H times nu, Planck's constant, which is 4.135 times 10 to the negative 15th electron volt seconds. Pardon me. 1 electron volt is 1.60 times 10 to the negative 19th joules. So an electron volt is the energy of 1 electron in a voltage gradient of 1 volt. All right, now, a little physics joke. If you ask a physicist what's new, he may say E over H, right? Because obviously if we divide both sides by H, it's equal to nu. That's a very old physics joke. So old you can't believe it. All right, so I just am constantly seeing things here that are annoying to me. All right, so when we talk about our frequency, our wavelength, and our energy, we have several different ways that we measure a wavelength. One is the amplitude. How far above or below our center line is it going, right? So for example, some of you may have a car that still has AM radio. Amplitude modulation is what that AM stands for, where the FM stands for frequency modulation, right? Now both of those have useful characteristics, which is why we have those two bands of radios. All right, but I digress. All right, so our sinuous curving line here represents a light wave. Its wavelength is the time that it takes to get from starting the light wave, coming through and returning to the same spot again. All right, so that is our wavelength. When we use electron volts for our energy, neither gamma or nu are very convenient. And eventually we want to get to voltage when we're talking about electrical devices. All right, so when we think about our frequency, right, which is measured in hertz or nu, when we talk about a red photon, it's 4.3 times 10 to the 14th. Our blue photon is 7.5 times 10 to the 14th. So that means in the same length, you can cram in a lot more blue photons than you can red photons. The wavelength in millionths of meters of red is 0.70. For blue, it's 0.40. The energy in joules for red is 2.9 times 10 to the negative 19th, whereas for blue it's 4.1 times 10 to the negative 19th. Therefore, what ends up happening is the energy in electron volts for red is 1.8 electron volts, and for a photon, and for blue is 2.6. Okay, so for blue, it's almost 150% more energy. Now, eventually, we'll get to the place where all of the energy that is coming down from the sun will be used to make electricity. For right now, though, we're really relying on the blue and violet parts of the spectrum to get there. All right, so our photoelectric and our photovoltaic effects, we have a photon. A photon is a little tiny packet of light. For a long time there was an argument, does light come in waves or does it come in particles? And so various experiments were done. Some seem to point towards waves, some seem to point towards particles. Eventually they decided, you know what, we'll just call it a wavicle and call it a day. All right, so we've got an incoming photon, right? It's from the sun, it's from the light, whatever. It comes in, it hits our valence band, and it emits an outgoing electron, right? And this band gap, right? We have a conduction band and a valence band, right? But this illustration is supposed to show how these are tied together. All right, so we get the photovoltaic effect from solids. We have a lot of energy levels so that electron can jump from our valence band to a conduction band if they have sufficient energy to leap the gap. All right, so when we think about different materials we might use, there's crystalline silicon. This is the one that is used in making photovoltaic panels. Right? Our symbol is C. SI. SI is the symbol for silicon on the in the chemical world. The band gap is 1.11 electron volts for crystalline silicon. Now, we can get even more if we use amorphous silicon, which they have as A-SI. Right there, the band gap is 1.7. But we may not be able to get the right kind of light in that'll make it jump that band gap. We have germanium, GE. It has a band gap of 0.67. Indium and antimonide. You'll notice indium is IN, but antimony is SB. Okay, fantastic. There, our band gap is 0.17. And diamond, which is just carbon that is stacked in what is literally the most boring way possible, has a band gap of 5.5. right? Now, when our light hits our solar panel, the band gap has to be close enough that the light creates the energy to jump the band gap. All right, so here we have the amount of spectral irradiance, in other words, the watts per meter per nanometers, and our wavelength in nanometers here. Okay, so you can see here in the UV or ultraviolet, we've got a certain amount going on. But here in the visible band, oh my God, we got a lot of energy, light energy coming in. And then that goes down. Here we're getting into the infrared. And in the infrared, the energy is trailing off. That may be part of why very few eyes are adapted to infrared. And I don't think people have any infrared capacity at all that I ever heard of. I know I don't. But there are certain animals that have mechanisms to sense infrared. All right, so as long as our photons have energies that are bigger than our band gap, we'll have electrons flowing. No, so the lower our band gap, the more of the solar spectrum we can use. And the more efficient is our photovoltaic device is going to be. So you'll notice here that it starts at the amorphous silicon level and goes up from there. And over here, oh bloody hell. Over here they say arbitrary units for the y-axis. Yeah, real helpful there, guys. All right, so our photon energy in electron volts has to be enough to jump the band gap. So how many devices can we put in series? In electricity, you may be familiar with the fact that you have two ways of hooking up electricity between devices. One way is to do it in parallel, right? So you would have a device where electricity is running here and one where electricity is running here, and they wouldn't necessarily be hooked up in a more complicated arrangement till later. Or you could do it in series where you have a device here and then you have a device here and they're hooked up head to tail. Inside our photovoltaic cell, we have a transparent negative terminal, right? So this is glass. The photons are going through. There is an N-type layer of semiconductor. Then there's a junction where it meets the P-type layer. And then you have a positive terminal off that. All right. So what is an N-type layer and what is a P-type layer? Bloody hell, they explained that to me 35 years ago, and I've forgotten since then. Being an industrial engineer, that just does not come up very often. All right, so we have a whole bunch of, we have different abilities for electrons to jump, right? And this again is an illustration of what this looks like sideways, right? So we have holes and electrons are jumping from hole to hole as the photo energy comes in. And then we have other free electrons that are going and filling the holes behind them. When we do that, we get our electron flow, which we call current. All right, well, solar heat is even simpler, and you have less efficiency loss with that. So more of the solar power is used when we use solar heat. All right, so we have the sun, we have radiant energy coming down, we have a solar panel, and usually that's a just a panel, a little box. It's got glass on the front for the sun light to go through. Inside is painted black, and it's got a pipe going through it where water is heated up. Or you can do it just with the air, but water would be a little more efficient. All right, so that water is heated up. It comes in here. We have a heat exchanging coil in the house so that you then are getting the heat back out of the water, and we're storing the extra heat to use later. Otherwise, it's going to get very chilly at night. Now, there are various ways you can do that thermal storage. I have kind of an old book on how to use solar power where they suggest that you fill your basement with rocks, you use the solar energy during the day to heat up those rocks as well as your house, and then at night the rocks give off the heat and keep your house warm. Although I think these days most people do it using water as the way to store the heat. Water is very efficient at taking in and releasing the heat. A long time ago, I worked with some guys who were selling solar systems like this, where they were actually capturing the heat into silicon oil, and then they were turning it back into a water heating system. The problem with silicon oil is you could put heat in easily enough, it's very hard to get it back out. Okay. Wind power is becoming very popular, and it is a pretty easy way to use green energy. Now, there are some limitations. The wind has to be blowing hard enough to make the wind turbine turn. But if it's blowing too hard, it may wreck the wind turbine. If you want to see some spectacular excitement, look on YouTube for wind turbine disasters, and you can get all kinds of footage of wind turbines where, for whatever reason, they couldn't put on the brakes and it just tears itself to pieces and catches fire, and oh, it's an exciting time. All right, so the maximum amount of the wind's kinetic energy is 1/2 rho times velocity squared. Rho is air density. If our effective cross-section of the windmill is A, and our wind flow rate is Q, we usually use Q for movement of all kinds of things. It can be the movement of heat, it can be the movement of water or air. All right, so Q equals A, the effective cross-section, times the velocity. The maximum amount of power we could get would be 1/2 rho times velocity cubed times A. Now, that would be the maximum amount. But as we know from the second law of thermodynamics, or the first law of thermodynamics, you can't win. So you can't get that maximum power out. So we put in CP. CP is the Betz coefficient, and it is less than or equal to 0.593. All right, so the power actually comes out to be P equals 1/2 CP times rho times V cubed times A. All right, so here we have an example of wind power. And we want to find out what wind speed is needed to achieve the windmill's design power output of 2.5 megawatts. All right, it's an exciting challenge. All right, so let me copy. Oh, this is where I was fooling around earlier, building my formulas. All right, so let's go ahead and paste. And all right, so I pasted that in here so that they call it a windmill, but damn it, I say wind turbine. All right, so we are given that the diameter equals 100 meters. All right. The minimum wind speed, V min, is 5.0 meters per second. Our Betz power coefficient, CP, I wonder why they use CP, because that is something that we use in quality control. Oh well, it doesn't matter. Is 0.50. And let's see, what else? Air density, okay. Rho equals 1.05, what is it? Kilograms per cubic meter? Yes. All right, so kilograms per meter cubed. Oops. And we want a power to 2.5 megawatts. All right, so, and I'm very worried, so I'm turning over here to make sure that I don't make a mistake. All right, well, we know that our ideal power is equal to 1/2 is equal to 1/2 rho times velocity cubed times area. All right, so we're going to translate that then into being equal to 1.05 right, and that is kilograms per meter cubed times 5 raised to the third, which is the minimum velocity, times here, maybe I should, oops, no, not that. So then we say, all right, but that is times our effective area. So that is 100 meters divided by 2. That quantity squared times pi, which I'm just going to simplify as 3.14, and that comes out as oh, okay, I see what I forgot now. I should have put 1/2 times. All right. There you go. All right. In your book, they say this is 5.15 times 10 to the 5th Newton meters per second. And of course, Newton meters per second is watts. Therefore, so the ideal power is 5.15 times 10 raised to the 5th power watts. All right, but that's the ideal power. When we calculate actual power, we have to include our Betz coefficient, which is 0.5. So 0.5 times our equals 0.5 times our power that would be ideal is going to be approximately 2.6 let's see, kilo. Oh, excuse me, it's going to be 0.26 megawatts. All right, so we're going to say this is watts, and we can summarize our answer as 0.26 megawatts from so our power varies directly as the cube of the wind speed. Therefore, we are going to say our velocity for not ideal, but how about nominal? Nominal is going to be equal to 2.50 divided by 0.26. That quantity needs to be raised to the 1/3 power. Okay, I need to put a left parenthesis there. All right, times 5.0. So to generate the design amount of power, we have to have 10.6 meters per second of wind. All right, so and let's save this to our introduction to engineering. Oh. Chapter 18, examples. All right, and I'll come here and I'll, oops. I'll make this a little clearer. Or I could go to a greater basic Latin. No, let's go for Greek. And where are my... Oh. Damn it. Don't want that. I want Greek letters. All right, well, it's just going to be obstreperous, and let's not spend all day fooling around with that. All right, so there we've worked our way through, rather tortuously, through the example of a wind turbine. All right, and we go to our the calculations that they do from the book, and And so we see they come up essentially with the same answer we did, but they go ahead and call it 11 meters per second. All right, so if we can just double the wind speed, that means we get 8 times the power because the velocity is cubed. All right, so our hydropower, we get indirectly because the sun evaporates water, carries it up to a high place where it can come back down again. A lot of hydropower, we have to have awfully big constructions to make that, right? So if you go and look at Hoover Dam or Grand Coulee Dam, or God help us, the Three Gorges Dam in China, they are huge constructions. Now, hydropower we can also use for load balancing, because in the electrical grid, we don't want a lot of highs and lows as far as the amount of electricity. That's not good for our electrical appliances. We want a very smooth production of electricity. All right, so dams can be enormous. Well, if you've ever seen a dam, you know that. A dam is totally dependent on its power for how high the water is. So if we had a very short dam, we wouldn't get very much power. We have the water here, it comes into the turbine here, turns the blades turn a generator, and that makes our electric power, right? And then the water goes out and continues down the river. All right, so this is Boulder Dam, and you can see it's a very impressive, construction. The amount of power that we produce is very straightforward. Here, you'll notice I put in a new equation because the old one was just so screwed up. The power is equal to the quantity rho times G times H times, you'll notice it's Q dot, which means it's the flow rate. And all of that is divided by G sub C. Now that assumes a 100% efficiency, when in fact most turbines are 90% efficient. Well, finding something that's 90% efficient, damn it, you're doing pretty damn well already. All right, so often the motors and generators in hydroelectric dams are reversible. So they can actually let the water flow down to make electricity, or they can use electricity to pump water back in. They give us this example where they say, suppose we have a small dam and a 10 megawatt generator. During the demand period of 6 hours, you could produce 10 megawatts. which essentially empties all the water from the impoundment behind the dam. During the night, 12 megawatts of excess power is available from the power grid. How many hours does it take to refill the dam if the pumping and generator steps are 100% efficient? Oh, man. All right, they don't have that example in the book. So it's obvious. Oh, wait. Well, let's go ahead and go for it. Our volumetric flow rate is Q1 for T1 hours. Okay, so that's 6 hours, and the power out is P1 for that T1 hours. So our volume of water is Q1 times T1. It is equal to Q2 times T2. And we know that power equals rho times G times H times Q dot, our flow rate, divided by G sub C. Therefore, our flow rate 1 divided by our flow rate 2 is equal to our power 1 divided by our power 2. So our power 2 for T2 hours is going to equal the flow rate, volumetric flow rate out, which is T2 for Q2 for T2 hours. All right, so we want the water from the dam during discharge to equal the water pumped back during recharge. Then our recharge time should be where T1 equals 6 hours. We can also, instead of saying our flow rate 1 divided by our flow rate 2 equals power 1 divided by power 2, by saying that our flow rate 1 divided by flow rate 2 equals our time 2 divided by time 1. Our time 2 is going to equal time 1 times 0.833, or 5.3 hours. How did we get that? We said because our power during the day that we're generating is 10 megawatts, and our power that we are using at night is 12 megawatts. Again, everything is assumed to be 100% efficient, which seems unlikely. All right. So there you go. Bob's your uncle. All right. So in summary, our we can get either electricity or heat from solar energy. We can use photovoltaic power made from sunlight, but backup of that power is difficult. Unlike our hydroelectric dams, we can't just pump water back upstream so that now we're ready for the next day. For a small solar installation, you could save power in batteries, but for these huge solar power installations, that hasn't been figured out yet. Heat is a very simple form of green energy. Anytime we can reclaim heat, we will be getting free power, because ultimately everything, all energy goes towards heat in the end. All right, wind power, well, they're saying it's a coming energy source. Damn it, I say it's here. And that is being used a lot. Hydroelectric power can give us electricity, and we can use to load level by those pumping techniques that we talked about. But again, it's hard to find a new place for a hydroelectric dam. Okay, any questions? I love asking that when there's no one here but me. Again, there are other forms of green energy that are being explored. I talked about using wave power or tidal power. There are other methods. For example, they've talked about using the differential in temperature between the surface of the ocean and the way deep part of the ocean. But that wouldn't be a very efficient way of generating power. In the same way that if we made a giant copper cylinder a mile tall, we could generate electricity from that, but again, not very efficiently, and those copper thieves would probably come and steal our cylinder. Anyway, please stay safe, keep socially isolated. We're getting through this, and we'll all be through it before you know it. Have fun now.